Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to look at cycloalkanes and cycloalkenes in the same 5 general sections, which is naming and writing empirical formulas, properties, drawing, reactions, and isomers. So we're going to start again with naming and writing empirical formulas, starting with kind of some simple ones. So the first one here, normally you don't see drawings like this very often, but the reason why I wanted to include it is to show that there's 2 hydrogens kind of off of every carbon, unless of course you have something different like a methyl group, for instance. Okay. Now a lot of the same naming rules apply. The biggest thing, or the 2 biggest things, are if you have one branch, and the fact that you have to have cyclo as part of the root of the name. So for instance, there are 5 carbons in this ring, or in this cyclo compound, and so this would be called cyclopent. Okay, so we have to add the cyclo in front of the main chain, which was 5, so cyclo, there's 5 in the main family chain, so cyclopent. Now, again, the ending here is just going to be simply an ane, because I do not have any double or triple bonds. Triple bonds in a cyclic compound are almost impossible because they have to have a linear shape around the 2 sides of the triple bond. You have to have a minimum of 8 carbons to make a cycloalkyne, making it very unstable. It's very reactive and just not very common. Okay. Now we do need to give this branch a name, so I do have a methyl group. So this is methyl cyclopentane, but I'm not giving it a location. Because this thing is cyclic, there's no really beginning and end, and because there is only one thing that is different on here, or one branch, the assumption that the methyl is on the first carbon. So it's considered redundant for you to say 1 methyl cyclopentane. But once you have 2 branches or 2 things that are unique, then we actually do have to start numbering them, and it's not considered redundant. Okay, so that would bring us to our second question, but I'm not quite finished with the first one. I wanted to do the formula for this compound here, and I wanted to talk about the generic formula for a cycloalkane. And we're going to get to it in isomers, but we're going to start looking at it here. When you have a cycloalkane, it has the same generic formula as a chain-ene, which is CnH2n. So in order for us to bring 2 carbons together to complete the ring, each carbon has to lose 1 hydrogen. So that's why we're used to, with an ane ending, there being a +2. But there isn't. In order for it to wrap around and actually connect into a ring, each carbon where it joins together has to lose 1 hydrogen. And so a cycloalkane has the same generic formula as a chain-ene. Okay, it's the same thing. So if I was to do this, I would simply count up the number of carbons. I've got 6, so this would be C6, right? We got pent is 5. Meth is 1, so C6, 6 times 2 is 12, and so the formula for this compound would be C6H12. So let's look at our next one. In our next one, we have a hexagon, which means that we have a cyclohex, and again, there's no double bonds in here, so this is simply a cyclohexane. Now, I picked this one specifically because there's a nuance that is very important for you to know. This obviously looks like a 1,2 or 1,2 prefix. Now, this is a methyl group, and this is an ethyl group. Now, because we have 2 carbons, okay? Now, a lot of people would just go, well, it doesn't really matter. The numbering is 1, 2. I don't really care. No big deal. It is actually a big deal. Before I assign the numbers though, let's talk about which order they should go in. So no matter what, we always have to go alphabetical order with our prefixes. So methyl is going to come second, okay? So it's going to be methyl cyclohexane. I need to have a number for it, so I'm just going to leave a space like this. And this would be ethyl. Ethyl has to go first because it starts with the letter E, and it needs a number, okay? So the rule is this, we need a tiebreaker. If you have the same numbering to keep the numbering as low as possible, the tiebreaker is the lower letter in the alphabet is going to get the number 1, and the larger letter in the alphabet is going to get the number 2. And what I mean lower is A would be the lowest and Z would be the highest letter. So E would be the lowest letter in this case. So this would officially be called 1-ethyl 2-methyl cyclohexane. And so what I'll do is I'll just erase that 2 there and that 1 here, and hopefully that makes sense. The same thing is true when you get a chain with a tiebreaker. Sometimes you will get a chain where one direction, you know, you might be a 4-5 or a 5-4. Again, if one's an ethyl and one's a methyl, the ethyl would get the lower of the numbers. But this is the only time that we really care about giving the lowest number to the lowest letter. We're always just trying to name organic compounds to give the lowest possible numbers. We don't really care if they go on an ethyl or a methyl or a prop, etc. Okay, the next thing we're going to do is we're going to write out the generic formula. So it's CnH2n. Let's count up the number of carbons. So an ethyl group has 2 carbons, a methyl group has 1 carbon, and a hex group has 6. So that's a total of 9. So this would be C9H2 times 9 is 18. Okay, and then I picked this one because we do want to talk about cycloalkanes as well. And there is a subtle nuance. Whenever you have a double bond in a ring, you must give it the numbers 1 and 2. So for instance, this is either 1, 2, 3, 4, 5, or this is 1, 2, 3, 4, 5. Now one way is more correct than the other. Because we have a methyl group, we want to keep the number on the methyl group as low as possible. So if we were numbering counterclockwise like this, 1, 2, 3, the 3 is lower than if we numbered it clockwise going this direction, in which it would be 5. So we want to do this counterclockwise, or sorry, counterclockwise. And so the name of this would be 3-methyl. Again, I'm making it 3-methyl, not 5, because 3 is smaller than 5. Then because it's cyclic, I have to have the word cyclo, so cyclo. There's 5 carbons in the main ring, so cyclopent. And then I have a double bond, so it needs to have ene. The thing is, ene, since it is already numbered 1 and 2, it has the highest priority. I don't have to say pent-1-ene. There is only cyclopentene, where the double bond has to be on number 1 and number 2. So it's considered redundant to put in 1-ene, and so we do not do so. Okay, the next thing we're going to look at is drawing a cyclic compound. And the first thing we're going to start with, again, is doing the formula. So this is an ane, but also cyclo. So a cycloane is going to be CnH2n. I then would count up the number of carbons I have. So I've got bute, which is 4. I got meth, which is 1. So this should be C5H10. We're going to draw it only 2 ways, a structural formula and a line diagram. Condensed structurals can be used for cyclic compounds. It's just very rare. And line diagrams sometimes are a hybrid between a condensed and a line diagram, so I'm going to talk about that as well. So our formula is C5H10. It's actually the molecular formula. Empirical probably isn't the best word to use there. The empirical formula is actually C1H2. So this is the molecular formula. Okay, so what I would do with a structural formula is I'd first draw my cyclic compound. So cyclobute, well, the simplest shape with 4 is, of course, a square, and so that's what I'm starting with. And then I need to add a methyl group to one of these carbons. I'm just going to put it off of this one. And then I have to make sure all the carbons are bonded 4 times. So the ones without the methyl group each need 2 more. Okay, those represent hydrogens. This one here only needs 1 more. And then the methyl group, of course, needs 3. So I always like to check if I've drawn it right by making one of the lines pink, and then I count clockwise from that position to make sure I have them all. I should have 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that one's good. I'm going to draw 2 different line diagrams because they're not too hard to draw anyways. So the first one would be simply, again, a square. And then I would have a stick coming off like that, representing the methyl group. But quite often you'll see a hybrid between a line diagram and a condensed structural. So for instance, the last one we named here, the main cyclic compound is line, and then they actually have kind of a condensed structural diagram coming off. So that's very, very common. You'll see that a lot. So I mean, I would accept both as a correct line diagram. So the first one is fine. But also if you wanted to actually put the CH3 group off of it, that is also a correct diagram. The next thing we're going to look at is isomers of cycloalkanes. I'm not going to go into ones of alkenes in too much detail here, but I will talk about them a little bit. So again, you kind of have 2 options when you're talking about cycloalkane and its isomers. As a cycloalkane, you must obey the CnH2n formula, and if it is a cycloane, there is no double bonds. Now the big thing is CnH2n formula is also used for alkenes in chain form with only 1 double bond. So if you count up the number of carbons there are in the compounds, and you notice it's a chain-ene or a cycloane, then they have to be isomers of one another. So let's say I had something like this. Here's cyclopentane, and I had 2-methyl bute-2-ene. Well, in both of these, I have 5 carbons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So the number of carbons is good, 5 and 5. And then I'm looking at the name and at the picture. So I recognize that a cycloane and a chain-ene give me actually the exact same formula. So this would be CnH2n, this would be CnH2n. And because they satisfy both the number of carbons, and from the name I recognize the generic formula, I know that these things would be isomers of one another. So again, a cycloane and a chain-ene were going to be the isomers of one another if they have the same number of carbons. Just as a double check if you want, what I can do is draw in the hydrogens. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens here. Here I would have 1, 2, 3, 4, 5, 6. This would have none. 7, 8, 9, 10. So these are both C5H10. These would be C5H10. Now when we get into a cycloalkene, things become much more complicated in terms of the number of options we have for isomers. Cycloalkenes are going to be CnH2n minus 2, which is the same as 1 triple bond in a chain which is the same as 2 double bonds in a chain, or a cycloene, which is a cyclic compound with 1 double bond in the ring format. All 3 of these things would have the same generic formula. So for instance, if I had a cyclopentene, that would also work with 1, 2, 3, 4, 5. This would be pent1-ine or pent1,3-diene. So again, maybe I'll highlight this. This is a chain with 2 double bonds. That's that one. We have a cycloene. That's this one. And we have a triple bond in a chain. That would be this one. Those would be isomers of one another as well. In terms of chemical and physical properties, they are extremely similar to chain alkanes, alkenes, alkynes. Because they're hydrocarbons, the only intermolecular force present is London dispersion forces. And of course, the bigger it is, the higher its boiling point due to a larger electron cloud. In terms of solubility in water, it's pretty much none. Again, these are nonpolar compounds, and so they do not dissolve well in polar compounds such as water, but they will have high solubility in nonpolar compounds. The only thing that's kind of unique is they're going to have a higher boiling point than their chain counterparts. So for instance, if I had 1, 2, 3, 4, 5, 6, this is hexane. Hexane would have a lower boiling point than its ring counterpart. So this would be cyclohexane. This would have the higher boiling point because cyclic compounds kind of stack like coins. They can get a better connection between the electron clouds between the compounds, and so they're a little bit higher. It's not drastically higher, but a cyclo compound will always have a slightly higher boiling point than its chain counterpart. In our last section, we're going to look at the reactions that cycloalkanes and alkenes undergo. And without surprise, you'll notice that they undergo very similar reactions to their chain counterparts. So cycloalkanes undergo a similar reaction as a chain alkane. So we don't dive into combustion very much anymore because we've been doing it for so long, but we'll revisit substitution and elimination. Those are 2 reactions that alkanes do undergo. So let's start with substitution. And when we were talking about alkanes, I talked about these as being a 1 in, 1 out reaction. Okay, and so what I mean by that is when we react our hydrocarbon with a small molecule, and in this case it's Cl2, I'm actually going to draw Cl2 as Cl in 2 different colors. Now, what you should recognize, even though this is a line diagram, there are 2 hydrogens coming off of every single carbon on every vertex, like this. So I'm going to add them in to give it a better visualization. What would happen is one part of the Cl2 would replace one of the hydrogens, and it really doesn't matter what it is, and one of the hydrogens will come out. So just for ease, I'm gonna color this one here as being pink, and I'm gonna say this Cl is gonna move in, and this H is gonna move out. So what's gonna end up happening is we're still gonna have a cyclopentane, but it is gonna have 1 chlorine off of it. I'm gonna color code it. So again, this is Cl, and then a byproduct of that is going to be HCl. The big thing I want you to remember is only 1/2 of the small molecule will enter the compound. So we would never have 2 Cl's on this thing unless I reacted 2Cl2s with it. So for instance, if this Cl2 had a 2 in front of it, it was 2Cl2, what I would end up with is another Cl somewhere on here. I don't know, I'm just saying maybe it's up here. And I would be left with 2 HCl molecules as the byproduct. For every chlorine I want to add to this compound, I have to have another Cl2 molecule. So again, if I wanted to say have a chlorine on every single carbon, on all of these carbons, there's 5 carbons, I'm going to need 5 Cl2 molecules, and I'm going to produce 5 HCl's. Still, only 1/2 of the original small molecule will enter the compound. The other type of reaction the cycloalkane can undergo is an elimination reaction. And in an elimination reaction, you are going to form a multi-bond. Okay. Now, again, what I'm going to do so you can visualize it a little bit better, I'm going to draw a bunch of hydrogens in. I am going to color code a couple of them. So in an elimination, we are going to eliminate 1 hydrogen from 2 different carbons. The hydrogens would not come from the same carbon. Generally, this is undone under high temperatures, maybe with a catalyst, in order to get this to happen. And so really we're focusing on these 2 carbons here. What would happen is the high temperature and the catalyst would allow for these bonds here to break. Each hydrogen would take 1 electron from the electron pair and leave. So it would take 1 of the 2 electrons in the electron pair and leave, and they would form hydrogen gas. So this would be HH, or H2 you could write it as. Either or, it doesn't matter. And then you're left with a cyclic compound that now has a double bond. So a double bond would form in that area. Please remember that it would never be 2 hydrogens from the same carbon. It would never be 2 on the same carbon. It would have to be 1 hydrogen from 1 carbon and 1 hydrogen from a neighboring carbon. So in this question, I just happened to choose these 2 carbons, but really it could be any 2. It could be this hydrogen and this hydrogen come together, or this hydrogen and this hydrogen. I've just drawn it like this for ease. Our very last one that we're going to look at is a reaction that happens in a cycloalkene. Enes and ynes really only undergo addition reactions other than combustion. So in an addition reaction, what we're doing is we're adding a small molecule, and in this question here, the small molecule is the Br2 into the double bond, where 1/2 of the small molecule goes to 1 carbon and 1 goes to the other. So again, what I'm going to do here is I'm just going to scratch this out, and I'm going to call it Br in 2 different colors so that you can see where everything goes. So what would happen is 1/2 of the Br would go to 1 of the carbons in the double bond. 1 of the Brs would go to the other carbon. That would break this bond and form a new bond between the carbons and bromine atoms, effectively getting rid of the multiple bond. So here we have cyclopentene, and what we're going to end up with is a 1,2 dibromocyclopentane. This would be called 1,2 dibromo, and we haven't got to halogens yet, but I think you can pick up why it's called dibromo. There's 2 bromines. Bromo is short for bromine. Di because there's 2 of them. Again, when we have 2 different things on a cyclic compound, we do have to number where they're located, keeping the numbers as low as possible. So 1,2 dibromo cyclopent, and now it's an ane. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.